Now, the last example is going to be involving the error involved when you use differentials. So differentials are used to make sure that things are within specifications. So that's a way that some of these homework problems are worded in terms of error. And the error is just the difference between the measurements. So you can have an error in the measurement of your function, and that's dy, or an error in the measurement of an input to your function, that would be dx. So let's look at this example. The edge of a cube was found to be 30 centimeters with a possible error in measurement of 0.1 centimeters. Use differentials to estimate the maximum possible error, the relative error, and a percentage error in computing the volume. So we want to find the error in computing the volume. So that means we just want to find the differential in the volume for a differential in the x value of 0.1 centimeters. So our dx is going to be 0.1. Our x value is going to be 30. And we're finding dy or dv in this case because we're talking about the volume function. So we start there with the volume function. V is s cubed, where s is the length of the edge of a cube. So remember the formula for our differential dv is the derivative of v times my differential for my input value, so times ds. So we were given that the edge was 30, so s is 30, and ds is the change in that input value, so that's 0.1 centimeter. We know that our differential dv is the derivative, which is 3 times s squared, times that difference ds, or 270 cubic centimeters. So this is the error in the volume, the maximum possible error in the volume when we have the possibility of an error in the measurement of the side of the cube of 0.1 centimeters. So that's the error is the differential of the function. The relative error is just this error as a fraction of the original volume. So in this case, the original volume of a cube, so suppose a cube is 30, suppose that side length really was exactly 30, then the volume is 27,000 cubic centimeters. So the relative error is this dv, the error that we found if we had an error of at most 0.1 centimeter in our measurement of the side, divided by the original volume. So that's 0.01. And then the percentage error is I just expressed that decimal as a percent, and that's 1%. So in summary, the differential is defined by the product of the derivative and dx. And the differential is just giving us an approximation for the change in a function value given a change in the input value. And then the linearization of a function we needed to figure out because we used that when we derived that differential. And that's just the equation of the tangent line at a point x equals a. And we can use that equation of the tangent line to approximate function values near x equals a because that tangent line is so close to our graph of the function near a.